Have you ever just stopped and wondered what actually makes something interesting? Not just complicated, but genuinely fascinating. Well, today we're jumping headfirst into a paper that tries to pin down that very idea. It's called The First Law of Complexodynamics by Scott Aaronson, Sean Carroll, and Lauren Ouellet. Hey everyone, welcome to CodeAccessHub. This is the place where we take on some of the biggest, most complex ideas in computer science and AI and make them something we can all wrap our heads around. And believe me, today's topic is a perfect example of that. Let's get into it.
So this is a big day for the channel. We're kicking off a brand new 30-part series exploring the fundamental AI papers curated by the one and only Ilya Sutskever. And we're starting with a really deep, fascinating look at the nature of complexity itself.
To get us started, the authors use this absolutely perfect everyday analogy, just pouring cream into a cup of coffee. I mean, think about it, right? At the very beginning, it's super simple to describe. You've got black coffee, you've got white cream, 2 layers. And at the very end, it's simple again. It's just a uniform, light brown liquid. But that moment in the middle, that's where the magic is. You get those beautiful, intricate swirls and patterns. That's the moment of peak interestingness. And that's the core paradox we're going to unpack. Now, this whole idea runs right up against a concept you probably learned in physics class. We're taught about entropy, right? Disorder. And the second law of thermodynamics says entropy only ever goes up. The coffee just gets more and more mixed, it never unmixes itself. But our gut feeling about what's complex, what the paper calls interestingness, well, that doesn't follow the same rule. It seems to rise up, hit a beautiful peak, and then fall back down into boring simplicity. So the question is, how on earth do you mathematically describe that bell curve? Okay, so to build a measurement for interestingness, we need a tool. And our starting point is something called Kolmogorov Complexity. Now, this is a seriously powerful idea. Basically, the Kolmogorov complexity of anything, let's say a string of ones and zeros, is just the length of the shortest possible computer program that can spit it out. You can think of it as the ultimate measure of compressibility. The more you can squish something down, the less complex it is. But here's the thing, if we just use that raw definition, we immediately hit a wall. Because according to pure Kolmogorov complexity, a string of pure random noise is the most complex thing possible. Why? Well, because there's no pattern, so you can't compress it. But does that feel right to you? Is a TV screen full of static really more complex and structured than, say, a beautiful painting? Our intuition screams, no way. Let's make this super concrete. Take a look at this ordered string. It's just 0, 1 repeated over and over again. The program to make this is ridiculously short, right? It's just a tiny little loop. So it has super low Kolmogorov complexity. Makes perfect sense. Okay, now look at this string. Imagine this was made by just flipping a coin a bunch of times. There's no pattern, no repetition, nothing your brain can grab onto. It's just noise. And here is the paradox in action. The absolute shortest program you could possibly write to generate that random string is basically just print this exact string. The program is just as long as the data. That means it has the maximum possible Kolmogorov complexity. And that just doesn't line up with our gut feeling that the coffee swirls are complex, while pure noise is just, well, it's just noise. So this leads us to the real challenge, the heart of the paper. How do we create a measurement that can see the meaningful structure in something while totally ignoring the random, useless noise? How do we get our tool to see the interesting swirls in the coffee, but not in the static? And the paper's absolutely brilliant solution is a new kind of metric they call apparent complexity. It's a clever little twist on Kolmogorov complexity that's designed to finally match our human intuition. The big idea here is that you first clean up the data before you even try to measure it. Think of it like taking a slightly blurry photo of the system. In physics, they call this coarse graining. You're basically deciding to ignore the exact position of every single tiny molecule, and instead, you're looking at the bigger overall pattern. Apparent complexity is just the regular old Kolmogorov complexity of that smoothed out, denoised version. And this slide just illustrates that perfectly. On the right, you've got some state with a ton of random noise all over it. Its raw Kolmogorov complexity would be super high. But if we do that coarse graining trick, if we blur our eyes a bit, we get that simple, smooth gradient you see on the left. The program to describe that smooth pattern is incredibly short. And the length of that short program, that's its apparent complexity. See, we're measuring the underlying structure, not the static on top. And you know, this paper wasn't created in a vacuum. Other smart people were wrestling with the same idea. You have Charles Bennett's logical depth, which says complexity isn't about program size, but about how long it takes to run. Then there's sophistication, which tries to separate the part of a program that holds the structure from the part that just holds random data. They're all different paths up the same mountain, trying to capture that elusive interestingness. So it's one thing to have a cool theory, but how do you actually test it? Well, the authors built this beautifully simple little model to simulate their coffee cup, and they call it the coffee automaton. It's basically a 2D grid with little particles representing the cream and the coffee. And here's where they do the key experiment. They ran 2 different versions of their simulation. In one version, the particles are like little ghosts. They just pass right through each other without a care in the world. But in the second version, they're like tiny billiard balls. They collide, they bounce off, they interact with their neighbors, and believe me, that one little change, it's everything. And here are the results. It's so cool. On the left, you see the non-interacting model. The green line, which is tracking complexity, just stays low and flat. Boring. But now look at the right, the interacting model. That green line does exactly what we hoped it would. Complexity shoots up, it peaks in the middle, and then it slowly falls back down, creating that perfect bell curve as the whole thing mixes together. This just brilliantly demonstrates the paper's central claim. It's the interaction between the parts of a system that actually generates those temporary structured patterns, the beautiful swirls and tendrils that our brains see as complex and interesting. Without that interaction, you just get a boring, predictable blend. Now, some of you might be thinking, wait a minute, isn't true Kolmogorov's complexity technically uncomputable? And you are absolutely right. So how'd they actually measure it? They used a really clever, practical workaround. They just used standard file compression tools, like gzip. They took a snapshot of each frame of the simulation, compressed it, and the size of that compressed file gives you a surprisingly good, real-world estimate of its complexity. And so this all brings us to the grand takeaway, the first law of complexodynamics itself. True complexity, the interesting stuff, isn't a final destination. It's a temporary, emergent phase that systems pass through on their inevitable journey from simple order to simple randomness. So why does any of this matter beyond a cup of coffee? Well, because it gives us a formal mathematical language for interestingness. It gives us a framework for understanding why our own universe, on its long journey from the super simple state of the Big Bang towards an eventual uniform heat death, has managed to produce these breathtakingly complex structures, like galaxies, stars, planets, and, yeah, even life itself. It's this profound bridge connecting physics, information theory, and computation. And that kind of leaves us with one final, absolutely mind-bending question to chew on. If all of reality is following this curve, this rise and fall of complexity between a simple start and a simple end, where are we right now? Are we still climbing the curve? Are we sitting right at its peak? Or are we on the long, slow, graceful decline? That's definitely a question for another day. For now, that's our look at the first law of complexodynamics. If you want to continue this journey with us and explore the next incredible paper on Ilya Sutskever's list, make sure you subscribe to CodeAccessHub. We'll see you for part 2.